Hello everyone. Before we move on to the subject of making oscillator circuits using op-amps, it's important to quickly review what is meant by frequency response or frequency selectiveness. Now, as the name suggests, frequency response defines how a particular system or a circuit is going to treat a signal of a given frequency, meaning given a system that takes an input xt and gives a signal yt. So this is a network made up of resistors, capacitors, or inductors. So how does such a system treat the given input signal depending on what is the frequency of this input signal? That is what is called h of omega. Speaking of sinusoids, if input signal is of the form cos omega t, right? And if I specify a particular value of omega, say cos omega mt. So depending on how this system treats different frequencies, or rather how this particular system treats the signal of frequency omega m, that is on which the output signal yt is going to depend on. So if you watch the video lecture on RC low pass circuits, you would see an example of how different frequencies are treated by a low pass RC circuit, where this system was something like this, right? R and C, and if we write the phasor representation of their respective reactances, we would get 1 upon j omega C and R, and we defined the gain of this system h of omega. Because the reactance is dependent on omega, that is frequency, the gain, that is output upon input, is also a function of frequency. That's why we call it h of omega. And if we use simple potential divider relationship, we would get 1 upon j omega c upon r plus 1 upon j omega c. This gives us 1 upon 1 plus j omega rc as the gain. Because this is a complex number, we could represent this to have a magnitude component and an angle component. So the magnitude component is this, and the angle component was found to be. Now, when we sketch this, meaning magnitude of the gain with respect to omega, this would be called the magnitude spectrum. That means if I was to sketch mod of h omega with respect to omega, this would be called the magnitude spectrum, and angle of h omega with respect to omega, this would be called the phase spectrum. If it just says spectrum, typically it would mean magnitude spectrum. So angle h of omega. Together, this spectrum is called the Bode plot. And for this particular circuit, if we plug in the values of omega equal to 0 and infinity, just to get an idea of how the magnitude of phase would look like, we found that at omega equal to 0, the gain tends to 1, and as omega is tending to infinity, the value tends to 0. So it looks something like this, right, where this value is 1. For this particular case, as omega tends to infinity, this tends to minus 90 degrees. At low frequencies, it tends to 0. And we took a whole example and showed how, if the input was of different frequencies, output would be attenuated to what extent and what would be the phase shift between input and output. Now, one thing to note here is that it's quite common to represent frequency instead of in a linear scale like 10, 20, 30, right? This is a linear scale. Instead of this scale, it is quite common to represent omega in logarithmic scale. That means arbitrarily, if I choose 1 here, then the next unit is 10, then the next unit after equal distance is 100. So 10 to the power 2, then 10 to the power 3, and so on. The advantage being that a logarithmic scale allows us to view percentage changes, right, or multiplicative factors. The shape of the curve will change. It looks something like this. This is arbitrary. This is not for a particular value. The only point is to show that the scale is now logarithmic. Right? Similarly, this also becomes a little more. Another common practice is to represent this gain, which is a ratio of output voltage upon input voltage for any given signal. It's common to represent this gain in dB. So instead of h of omega, what you have is 20 log of h of omega, and the unit now is in decibels. If that is the case, then this point, when h of omega is equal to 1, in dB, it becomes 20 log h of omega, that is 20 log 1, which is 0 dB. So this point, gain in dB, would be 0 dB. That is the maximum gain. That's the condition of maximum gain, 0 dB. For angle, you can represent it in radians or in degrees, doesn't matter. Now comes into picture the concept of bandwidth. Now, in an earlier discussion session, we've discussed that bandwidth is that range of frequencies for which the gain remains constant or nearly constant, right? So what should be that range? Here comes into picture the concept of cutoff frequency. Okay. Now, the moment we are calling it a filter, that means we are referring to its ability to allow certain frequencies to pass unattenuated, while other signals which have, say, some other frequency, their gain will be reduced by a certain amount. Speaking of cutoff frequency is that frequency at which the power of the output becomes half of that of input. Right? That means output power is half of the input power. Meaning the ratio of output to input power is 1 by 2. If in terms of power the ratio is 1 by 2 and power is square of voltage, this would mean that in terms of voltage, the ratio of output to input voltage should be 1 upon square root 2, because power is square of amplitude. That means whatever was the input voltage, the output is 1 by root 2 times that voltage. So if I was to consider gain, not in dB yet, so if we were to consider the magnitude value, that would mean that output upon input becomes 1 by root 2, that frequency. So that omega, say at omega c, where this happens, this is called the cutoff frequency. Now this is not in dB, this is just a ratio right now. 20 log, this would mean 20 log 1 by square root of 2. This would mean minus 20 log of square root of 2, that is 1.414. This would give us about 0.15. When you multiply, this would give us minus 3 dB. So another way of saying what is cutoff frequency is that where the gain of the system drops by 3 dB. If we assume that the maximum gain is 0 dB, the point where this falls by an amount of 3 dB, so it falls to minus 3 dB, the frequency where this happens, which is called 3 dB point or minus 3 dB point, This value of frequency is called the cutoff frequency in radians per second. So there are three ways of explaining what is cutoff frequency. One in terms of power, that says the point where which power falls by 50%. In terms of amplitude, it is that frequency where amplitude has dropped by a factor of 1 by root 2. That means gain wise, where gain becomes 1 by root 2. The third way, when gain is expressed in dB, it is that point where gain falls by 3 dB or gain becomes minus 3 dB. This is called cutoff frequency. Now, as said earlier, the range of frequency for which the gain remains almost constant, that is called the bandwidth. So typically, this range of frequency for which gain is above minus 3 dB, this is called the pass band. And for a low pass signal, this would also be the bandwidth. So this range is pass band, and this range of frequencies, this is called stop band. So obviously it's not that after cutoff frequency, the signal is multiplied with a factor of 0. No, it's multiplied with certain factor, but that factor is significantly low. And we saw how that works in the example which was there in the earlier video lecture. If we selected a frequency somewhere here, for which the corresponding gain is say minus 10 dB or minus 5 dB, minus 5 in dB would correspond to how much in magnitude? That means output for this particular frequency where gain had fallen down to minus 5 dB, their output is actually 0.56 times input. Means just a little above half of the input, right? So the output magnitude is significantly attenuated. If the maximum gain was 1, we'll allow it to fall up to 70.7%, almost 71% we'll allow it to fall, beyond which we will consider that the gain is too less and that is beyond the cutoff frequency. This is important to understand that when we say filter and we use words like pass band and stop band, it does not mean that this is like exactly this is the range of frequencies that it will allow to pass, and beyond which, beyond the cutoff frequency, no frequency is going to pass. No, that's not what will happen, because we have seen in an example that it's as simple as saying that for frequencies less than the cutoff frequency, it will be multiplied with a large amount of gain, which is close to 1, minimum being 0.707. Beyond the cutoff frequency, the gain is significantly low. And that is why we say those frequencies will be significantly attenuated in the output. Of course, ideally, if we wanted only up to a certain frequency to pass and all frequencies beyond it to be suppressed, we would need a filter that looks like this, whose frequency response looks like this, right? And this is what is an ideal low pass filter. Okay, so ideally that is how a filter would look like, but we are talking about practical filters which are made using R, L, and C elements, and this is how the frequency response of such a filter would look like. We can of course make a practical filter come closer to this ideal nature if we can somehow make the roll-off near the cutoff frequency steeper. This can be done by increasing the order of the filter, by connecting more stages, or by using other various types of filter designs like Chebyshev filter or Butterworth filters. So again, to rephrase the definition of bandwidth, bandwidth is that range of frequency up to which gain falls by 3 dB. Okay, that means in this case, this is the bandwidth of this signal. Of course, in hertz. So bandwidth is again that range of frequencies for which gain is nearly constant. It's having a maximum value, maximum gain, allowing it to fall up to say 70%. That is the minus 3 dB point. What is the value of omega c for this particular circuit that we've been talking about? All we need to do is plug in h omega equal to 1 by root 2. That means H omega for this particular circuit was found to be 1 plus omega square r square c square. This equal to 1 upon root 2. So, right, when we solve this, we'll find that omega equals to 1 upon rc. So the cutoff frequency omega c, where this relationship is true, that means where gain is equal to 1 by root 2, that particular frequency can be calculated as 1 upon rc. In hertz, its value would be 1 upon 2 pi rc for an RC low pass filter for a circuit like this, right, where this is input and this is output. Now, another very important aspect to understand here is the phase spectrum, right? That is this spectrum. We notice that this phase difference between the output and the input also changes as frequency changes. That means at the cutoff frequency, meaning at this point, what should happen? What was the angle? Angle was minus tan inverse omega RC. So when you plug in omega equal to 1 upon RC, you get minus tan inverse of 1, that is minus 45 degrees. Right? And we see that as frequency increases, the phase shift between input and output goes on increasing, and the maximum phase shift that you can have is minus 90 degrees. Right? So one such network can give us a maximum phase shift of minus 90 degrees. This is another important thing to note. Now, this is the circuit that we are talking about right now, where R and C are in series, and we are measuring the output across the capacitor. If we just inverted the positions of R and C, that means we now consider a circuit like this, where this is where we give the input and this is where we measure the output. This is still R. The reactance is 1 upon j omega c. For such a circuit where we've just inverted the position of R and C, for such a circuit, and you can derive this, you will get h of omega to be j omega rc upon 1 plus j omega rc. You can find its magnitude and its angle separately with respect to omega, and this is how its spectrum would look like. Now this is in logarithmic scale already. Remember, for the previous case, we had got a spectrum like this. For this case, we will get a spectrum like this. The maximum gain is 0 dB. So let us call it mod h of omega, but in dB, the angle h of omega, which is now in, say, radians per second. For this particular filter, you plug in the values, you calculate what would be h of omega and what would be mod h omega. You plug in and see what happens at when omega tends to 0, what happens when omega tends to infinity, and you'll find that the phase would look something like this. That means as omega tends to 0, angle tends to 90 degrees. As omega tends to infinity, phase tends to 0 degrees. What we can see from the frequency response is that, say, this is the point at which gain falls to minus 3 dB. For all the signals having frequency above this cutoff frequency, they will be allowed to pass with negligible attenuation, whereas those which have a frequency less than this cutoff frequency would be multiplied with a very low gain. That means they'll be attenuated. Allows large frequencies to pass unattenuated. So this is a high pass filter. The maximum phase shift that you can obtain using this kind of a network is plus 90. So there would be some frequency where this becomes 60 degrees, some other frequency where the phase difference is 30 degrees. That means if we wanted a phase shifting network, that means if we wanted a circuit where output lags the input by a certain angle, or where the output leads the input by a certain angle, there also we could use such an RC network, right? Depending on how much of phase shift do we want the circuit to produce. So these circuits, these RC circuits, so these are frequency selective networks. They behave in a different way for different frequencies. Similar kind of nature can be derived for RL circuits or for RLC circuits, and they could be used as low pass filters, high pass filters, band pass filters, that means filters that allow a certain band of frequencies to pass, and attenuates frequencies which are lower than some lower threshold and greater than some upper threshold. So allows a band of frequencies to pass. They can also be used to make band reject filters. That means outside a certain range of frequencies, they would be multiplied with a large gain, and within that range of frequencies, they would be multiplied with a low gain. Those are called band reject filters. So this is why circuits made up of R, L, and C elements are called frequency selective networks, particularly due to their ability to produce a gain which is dependent on frequency, and more importantly, a phase shift which is dependent on frequency. We'll look at an application when we talk about oscillators in the next lecture. Thank you.